Hello and welcome to Empowered Learning. This is the second video in the video series on the topic of power series. So in the first video, we were introduced to what a power series is in general. We talked about the four basic characteristics of a power series, and we saw how to actually evaluate a power series to see whether it was going to be convergent or not, and if so, what interval of x values would force a power series to be absolutely convergent. And then we took the interval of convergence after finding the radius of convergence and test the endpoints to see are the endpoints of the interval of convergence, do they actually produce a convergent infinite series as well. Okay, so we're going to do more of that in this particular video. I have two examples for you. The difference is that I don't have these already worked out, so we're going to work these out from scratch. So in the introduction, I kind of wanted to, avoid having to go through all the minutia and calculations and whatnot. But for those of you that actually need to see me go through that step by step, this is the video for you. All right, so we're taking this power series that we have here, and we want to find out what is its radius of convergence as well as its interval of convergence as well. And remember that what that means for us is that once we find the IOC prime, which we know by default, depending upon what case we have, but let's say if we have a case 3, then we're going to have this A minus R to A plus R, where A is going to be the number that the power series is centered about, and R is going to be the length of the radius of convergence. Now, let's go ahead and get this out of the way now. Again, we know that within a power series, we know that it's on the inside of it, it generally looks like this. And so since we just have an x to the n here, we know that A has to be 0. Okay, so we know that this particular power series is centered about the value A is equal to 0. So what that tells us here is that if we have a case 3 situation, that our interval of convergence, or IOC prime, is going to be from minus R to R. So once we find out what our radius of convergence is, we just know it's going to be plus or minus that if we have a case 3 situation. All right, so first thing is we need to find out when is this particular power series going to be absolutely convergent. Okay, so to do that, in this case, since everything is not raised to the power of n, we want to use the ratio test. Okay, so we're going to say use ratio test. And essentially what we want to find out is when the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, whatever expression we get in the long run, we want that to be less than 1. Okay, so first things first, we need to identify what a sub n is, and that's just going to be what our sequence that makes up the series is itself. And so that's what that is. Now the a sub n plus 1, everywhere where we see n, we're going to replace it with n plus 1. Okay, so here we'll say negative 1 raised to the n plus 1 times x raised to the n plus 1, all that over 4 raised to the n plus 1 times natural log of n plus 1. Okay, so from here, we need to essentially take the absolute value of a sub n plus 1 divided by a sub n. Now, to make life simple here, our alternating factors here, the negative 1 raised to the n plus 1 and the negative 1 raised to the n, they're essentially going to be stripped out, and everything else is going to pretty much stay the same. So I'm going to write these, but I'm going to exclude this and exclude that because the absolute value is going to take those away. Okay, so Now that we have that, I'm going to write down my a sub n plus 1, which is just going to be this. And we're going to multiply that times the reciprocal of a sub n here. So that's just going to be 4 raised to the n times natural log of n, all that over x raised to the n. Okay. Now, note that this x raised to the n plus 1 here, we can rewrite that as x raised to the n times x, or x raised to the 1, which will just be x. And this 4 raised to the n plus 1 will be 4 raised to the n times 4 raised to the 1. Okay. And here we also have natural log of n plus 1. And then we'll multiply that times 4 raised to the n times natural log of n, all that over x raised to the n. So here we see that this x raised to the n and this x raised to the n will reduce to 1. This 4 raised to the n and this 4 raised to the n will also reduce to 1. And so what we end up having left here is this x, a 4, natural log of n, and natural log of n plus 1. And so here I'm going to go ahead and put those absolute value signs back in because this is going to be important. Just wanted to start off by stating here that the -1 raised to the n factors were going to be eliminated. So I didn't feel like writing all that. All right, so now that we have this, we're going to rewrite what's left and then take the limit of it. So here we have, this is x times natural log of n all over 4 times natural log of n plus 1. And it's going to be absolute value of all of that. And we'll just leave it like that. So this is what we need to take the limit of. Okay. So if we take the limit of this, what I'm going to do to make this a little bit easier for me is I'm going to split this up as 2 separate absolute value functions here. This will make it easy for me to evaluate the limit. So now that we have it like this, then we can just take the limit as n approaches infinity of a sub n plus 1 divided by a sub n, and all that's going to equal limit as n approaches infinity of absolute value of x over 4 times limit as n approaches infinity of natural log of n over natural log of n plus 1. Okay, so for starters, we know that this absolute value of x over 4, since n is the limit operator's variable, the x and the 4 both look like constants. Okay, so if we evaluate this limit here, a limit of any constant is just the constant. So this is just going to be absolute value of x divided by 4. Okay. Now, for the second factor, we know that if we plug in infinity for n, for the natural log of n and the natural log of n plus 1, we know that we're going to get infinity in both cases. And so we have an infinity over infinity case, which tells us that we could use Hopital's rule. Okay, so if we use Hopital's rule, of course, we're going to carry over the fact that we have this constant absolute value of x divided by 4 there. But now we need to take the derivative of the numerator and denominator separately here. And that's just going to be 1 over n, and a derivative of natural log of 1 plus n via the chain rule is also going to be 1 over n plus 1. And so now from here, we can kind of see the light at the end of the tunnel. So we still have absolute value of x divided by 4 times, and this will be limit of 1 over n times n plus 1 over 1. Sorry, didn't mean to put an n there. And of course, all that is just going to end up being just n plus 1 over n. So I'm going to go ahead and erase that and just replace all of this with just n plus 1 over n. And of course, from there, we know here we could rewrite this as 1 plus 1 over n, or we can look at this and say, all right, the limit of n plus 1 over n is just asking us, does this sequence have a horizontal asymptote? And it does at, we're going to say y equals 1. So here, we're going to take all of this, and we know that that limit is just going to be 1. So the result that we have is just going to be absolute value of x divided by 4. And of course, what we want to know here is we want to know when is this particular limit here going to be less than 1. So what we want is, when is that going to be less than 1? And essentially what this means here is that absolute value of x is going to be less than 4, which means that x is going to be in between -4 and 4. Okay. And so our interval of convergence prime, the initial one here, is just going to be from -4 to 4. Okay. So these are the x values that we can plug into our original power series here, and we know that they're going to converge. Now, what we have yet to see here is what happens when x is -4 and when x is +4. Okay, are we going to have convergent or divergent series pop out as a result of that? So that is what we need to check on next here. All right, so we're going to go ahead and check out when x is equal to -4. We're going to use our series here. So what we're going to end up having here, let me try that again. So we have this particular series here, and we're going to have a -1 raised to the n times, in this case, a -4 raised to the n over 4 raised to the n times natural log of n. Okay. And if I do some rearranging here, let's try to make that sigma sign again. Then this -4 raised to the n, this could be looked at as, and I'm going to write it here actually, we could rewrite this part as a -1 raised to the n times 4 raised to the n. Okay. And so if we look at it like that, then this -1 raised to the n times this other -1 raised to the n could be like a -1 times a -1, all that raised to the n, which is essentially just a 1 raised to the n. We also see here that this 4 raised to the n and this 4 raised to the n will reduce to 1. So that part will go away, and here in the denominator, what's just going to be left after that is just natural log in here. Okay. And of course, this 1 raised to the n, that's just going to be 1. So we could just replace all of that with just 1. So we essentially have a series here that's just going to be series of 1 divided by natural log of n. And we want to know, is this particular series going to converge or diverge? So a good idea for this particular series to test for its convergence or not is to do the comparison test. And so I'm choosing that because if we were to take the limit of what we have here, if I plugged in infinity in for n into the natural log, a natural log of infinity would be infinity, and 1 divided by infinity in terms of limits is going to 0. So of course the nth term test for divergence is inconclusive. And so what we need to do now is try to compare this series to one that we know of that either converges or diverges. So the first thing that we want to look at here is the fact that if we're looking at, let's say, natural log of n, or let me just do this in general first, and then I'll go back to the sequence. So let's take the function natural log of x. That function in general here looks something like this. Okay. Now, let's also consider the function y is equal to x. Okay, so I'm just going to do both of these. And y is equal to x, that function looks like this. The point that I'm trying to make here is that I know that my function y is equal to x is always going to grow faster than natural log of x. Okay. So in terms of these series here, I could consider the series 1 divided by n, and of course n is acting like x is over here. So if I wanted to consider this series, okay, I can compare this series and I could compare this series. Now, of course, we know this particular series as the harmonic series. And we know, well, the harmonic series minus a term, okay? So this would be like, well, the actual harmonic series would just be 1 plus this, okay? But regardless here, we know that this ends up diverging, okay? Now here, we're still trying to figure out if this one converges or diverges, but we have a situation here where we have two series that we can compare. And of course, the direct comparison theorem says that if we have a series that is larger than the one that we're considering, then if that larger series diverges, then the smaller one diverges. If the larger series converges, then the smaller series converges as well. And so, unfortunately, in this particular case here, this is the larger series and it is diverging instead of converging. So we have to go to what it says about divergent series. So the direct comparison test says that if we have a series that is smaller, that's the smaller of the two that we're comparing, and that smaller series diverges, then it means that the larger one does as well. Okay. Unfortunately, again, we have the larger series that is diverging, not the smaller one. So in this instance, we can't use direct comparison test. However, we can use the limit comparison test. So the limit comparison test tells us that if we do the limit of a sub n over b sub n, and based upon what value of c we get different outcomes. Okay, so, and I'm just going to put c here. Okay, so we want to know what the limit comparison test says. Again, we have a lot of different outcomes here. So let's go take a look back at what the limit comparison test actually says here. So if we're talking about the limit comparison test, if we do the limit of a sub n over b sub n, where a sub n is the original sequence within the series that we're trying to deal with, and the B sub n is the one that we came up to compare it with. If our limit value ends up being something that is positive, then we know that either both series converge or both diverge. If we actually end up getting 0 for it and the B sub n series converges, then it means that the A sub n series will also converge. Okay. Essentially what that's saying in this case is that if our limit ends up being 0, then our B sub n series is larger than our A sub n series. And if the larger series converges, then the smaller series converges as well. Okay. And of course, if we get plus or minus infinity, or if our B sub n, or the B sub n series, the one that we came up with, diverges. So if both of those things happen at the same time, then we know that the series with A sub n also diverges. And remember, again, the series with A sub n was the original one that we had before we started doing the comparison test, and the B sub n is the one that we made up to compare it. Okay, and of course, if we get C is equal to 0, and our B sub n series diverges. So if we have both of those situations here, or if we have C is equal to plus or minus infinity and the B sub n converges, which is the opposite of what we had here in situation, or what is it, number 3 here, then for both of those situations, we know that the test is inconclusive. Okay. So if we have situation number 1, number 2, or number 3, if we have any one of those 3 situations there, then we kind of know what the answer is. If it deviates from one of these 3, then of course the test is inconclusive. All right. So now we see what it is that we need to compare here. And of course, what we are going to call this one, this is going to be the B sub n for the limit comparison test, and this is going to be the A sub n for it. Okay. And so all this is to say that we need to use the limit comparison test, and now we know why. So I'm going to erase all of this and just state, hey, what's going to be my 2 series that I'm going to compare, and then take the limit of it, and then we're going to move from there. All right, so I've gone back here and I've went ahead and stated what my A sub n and what my B sub n are. I've put little dashes over it just to make the A sub n and the A sub n here different than the A sub n that I defined up earlier in the problem. So what we want to do now is take the limit as n approaches infinity of A sub n dash over B sub n dash. And so we're going to say here, our A sub n is just going to be 1 divided by natural log of n. And our B sub n, we're just going to do the reciprocal of that, which is just going to be this. And we have limit as n approaches infinity over n over natural log of n. Now, if we were to plug in infinity for n both in the numerator and denominator, we would end up having infinity over infinity, which we know is an indeterminate form that allows us to use Hopital's rule. And Hopital's rule basically states here that we take the limit as n approaches infinity, take the derivative of the numerator and denominator separately. And so the derivative of the numerator is just going to be 1. The derivative of the denominator is just going to be 1 over n. And this just ends up being the limit as n approaches infinity. Yeah, sorry, I had to stop the video there for a second. The limit as n approaches infinity of n. And of course, that's just going to go to infinity, which basically tells us that we have a situation here where our series is going to end up diverging. Now, we know that our corresponding series that we were looking at here, which is this one, by the way, we know that this particular series is going to diverge, because if we go back and look at our A sub n and B sub n and the corresponding series that go with it, we'll go back here. We have a case 3 situation here where our C ended up being positive infinity, and our series made up of the B sub n, in this case, which was the harmonic series, that we know diverges. So we have both of these conditions being met. So that means that the series that we were actually trying to figure out whether it diverges or not, converges or diverges, is going to actually end up diverging. And so that's how we're able to say that. So when x is equal to -4, that is going to produce a series here that is going to be divergent. Okay. And so that's what we'll state here. And then we'll test out when x is equal to +4. All right, so I've already written here that the series that we were considering, which was right here, the series made up of the sequence 1 divided by natural log of n, and that happened when x is equal to -4. It diverges, which means that x equals -4 is not in our interval of convergence. So now what we need to do is see what happens when x is going to be equal to +4. We'll see what happens here when x is equal to +4. The series that we end up coming up with here have -1 raised to the n, and instead of having a -4 here, we will have a +4, 4 raised to the n, and this will be divided by 4 raised to the n times natural log of n. Bring that down a little further. All right, and so here we know that these 4 raised to the n's here will reduce to 1. And what we will end up having here is an alternating series, -1 raised to the n over natural log of n. Okay. So we see here that we have an alternating series. So it's natural for us to go ahead and use the alternating series test to see if this particular series would be conditionally convergent by the alternating series test. So to do that, the first thing that we would want to do is we want to look at the non-negative version of this. So I'm going to write this way just so that we're all on the same page here. So let's say -1 raised to the n times your b sub n. And your b sub n in this case is just going to be 1 over natural log of n. Okay. So for the alternating series test, the first thing that we have to show here is that b sub n plus 1 is less than or equal to b sub n. And in this case, this will be for, we'll assume n is greater than or equal to 2. Or really, it doesn't have to be this, but it's going to turn out to be this as well. So just to keep it general, I am just going to say this, just to be all-encompassing and correct here. So we want b sub n to ultimately decrease. So that's really what we're trying to say here. Okay. The second thing that we need to do is figure out, does the limit as n approaches infinity of b sub n go to 0? If both of these conditions are met, then we know that our alternating series will converge conditionally based upon the alternating series test. Okay. All right. So if we list some values of b sub n here, so we have b sub 1, that's just going to be, oh, sorry, not 1, 2. Yeah, let me we have to start here at 2. So this would be natural log of 2. Okay. And then we'll have b sub 3 is natural log of 3. B sub 4 is natural log of 4. Now, of course, knowing that the graph of natural log looks something like this, where we have an asymptote here at x equals 0, of course, natural log of 2 is going to be smaller than natural log of 3. And natural log of 3 is going to be smaller than natural log of 4. So in turn, 1 divided by natural log of 2 is going to be a number larger than 1 divided by natural log of 3, which is going to be a number larger than 1 divided by natural log of 4. Okay, so we see here that because we have 1 divided by a number, that for the corresponding function is always going to be increasing, we're going to be getting smaller and smaller numbers. So this definitely does meet this condition here for the alternating series test. Okay, so first one checked. Second one, we see here that the limit as n approaches infinity of b sub n, which is 1 over natural log of n. As we discussed before, whenever we were testing when x is equal to -4, if I was just to put an infinity here, I know that natural log of infinity, although it would do it real slow, it would be going to infinity here. And of course, this would approach 0. So we have both of these conditions met. So we can say that this particular series, so therefore the series here it will conditionally converge via the alternating series test. And what that means for us is that we can actually include x equals 4 in our interval of convergence, or it is an x value that will produce a convergent series here. So x equals 4 in IOC. So now we know, therefore, so we're done with all this. So we know that the IOC, the true IOC for our series that we began with at the very beginning of this problem, that is going to be this particular interval here, where when x is -4, it's not included, but when x is 4, it is included. And the ROC, or R, is just going to be 4. Okay. And again, that is for our original series that we were working on here. And I'm going to circle it just to make sure we recognize that. So that was the series. We know that its radius of convergence is 4. Its interval of convergence is going to be from -4 to 4, where we are only including +4, okay, and excluding -4. And so that is what we needed to know for this particular given power series. All right, so we're going to look at one more example, and then we'll move on to the part 3 video, where we'll go a little deeper with the power series. Okay, so for our second example here, we're going to do the same thing. What we're looking for is the radius of convergence, and we're also looking for the interval of convergence. So these are the two things that we are looking for. And so here for this one, we're going to start off by using the ratio test and try to prove absolute convergence. And we're going to do that because we don't have all of our factors here in the sequence that's making up this series all of them not raised to the power of n, or n, n times something. So the ratio test is good for this one. So we're going to say, I'm just going to put ratio test here. So we have our a sub n, which is, trying to get control of this pen here. This will be the 3x minus 2 raised to the n over n times 3 raised to the n. And we have a sub n plus 1. Everywhere where we see n, we replace it with n plus 1 here. Okay. And for here, I'm going to rewrite the a sub n plus 1 as just 3x minus 2 raised to the n times 3x minus 2. All that over n plus 1 times 3 raised to the n times 3. Okay. And so we need to figure out what the absolute value of a sub n plus 1 divided by a sub n is. And we're just going to write down the a sub n plus 1, multiply it times the reciprocal of the a sub n. All right, so I've already written that down. The a sub n plus 1 is this first factor here times the reciprocal of a sub n. And so now we just need to simplify what we can. So this 3 raised to the n, 3 raised to the n, that's going to reduce to 1. This 3x minus 2 raised to the n, and this 3x minus 2 raised to the n is going to reduce to 1 as well. And I believe that is all we have. So when we write what's left in the numerator, this will just be n times 3x minus 2. In the denominator, we're going to have 3 times n plus 1. Okay. And since we know that we're going to take the limit of this as n approaches infinity, everything with n I'm going to put together. Everything that does not have n, I'm going to put together. So we have this 3x minus 2 over 3. Since this is absolute value here, we wanted to do it like this, times absolute value of n over n plus 1. Okay. So therefore, when we take the limit as n approaches infinity of this a sub n plus 1 divided by a sub n, let's see here. So here we know, since x looks like a constant to this limit operator, we can go ahead and put this 3x minus 2 divided by 3, absolute value of that, all on the outside. And then we'll have limit as n approaches infinity of the absolute value of n over n plus 1. And again, here we know that the limit of absolute value of n over n plus 1 is just asking, does this function absolute value of n over n plus 1 have a horizontal asymptote? And it does at y equals 1. So this whole limit here is just going to 1. And all we have left there is essentially just absolute value of 3x minus 2 over 3. And I'm doing that because the absolute value of 3x minus 2 over 3 can be absolute value of 3x minus 2 over absolute value of 3. And of course, absolute value of 3 is 3. Okay. And we know here that this must be less than 1 in order for us to have corresponding infinite series from the power series that is convergent. So since we have this situation here, therefore, this means that we have absolute value of 3x minus 2 has to be less than 3, which means that 3x minus 2 has to be in between 3 and negative 3. And of course, if we solve for x, if we add 2 to both sides of this inequality here, so negative 3 plus 2 is going to give me a minus 1. And 3 plus 2 is going to give me a 5. And then we finish out by dividing both sides by 3. And we see here that x is going to have to be a number strictly in between negative 1/3 and a positive 5/3. Okay. So what this tells us is, of course, our interval of convergence is going to be from a minus 1/3 to 5/3. It turns out here that our radius of convergence is actually going to be 2/3, and I'll show you why that is if you don't see it now. And this also means that our A, which is the number that this particular power series is centered about, is going to be 2/3 as well. Okay, so I'm going to come back up here for a second and talk about why this particular power series is centered about 2/3, and that the radius of convergence is going to be 2/3 as well. So if we come and look at what we have here, notice that this 3x minus 2 raised to the n, if I wanted to, I could factor out a 3 out of that, okay, out of this 3x minus 2. If I did that, then I would have 3 times x minus 2/3, and all of that would be raised to the n, which means I would have 3 raised to the n times x minus 2/3 raised to the n. And notice that this portion here meets the x minus a criteria that we have for a power series. And of course, this 3 raised to the n part is just another piece of that works out here. So if I was to take this now and divide it by n times 3 raised to the n, and do that here. Let me erase this. And do that here as well. You'll see that these 3 raised to the n's would reduce to 1. And what I would actually have is this situation here. Okay. And so this is another form of what we dealt with here when we did the ratio test here for our a sub n. We just kept the factor of 3 in there. Okay. And again, we see here that we in the numerator we should have something that looks like x minus a, so that a is going to be the 2/3 there. Okay. So if we look here, and I think I wrote something wrong down here, by the way. This radius of convergence here, it's not 2/3. So I was thinking about what this number was here, the value that the interval of convergence was centered about. Okay. So what the radius of convergence would be here is it's just going to be half the distance from a negative 1/3 to 5/3. Of course, if we took the distance from negative 1/3 to 5/3, that's going to be 6/3, which is the same as 2. And of course, half of that is going to be 1. So that is actually what our radius of convergence would be. And if we come back up here, I'll show that. If we're centered here at 2/3 and I go 1 unit in this direction, we know 1 is the same as 3/3. So if I was to add 2/3 to 3/3, I would get 5/3 here. And then of course, if I was to come here and subtract 3/3 from 2/3, I would get a negative 1/3. And so that's how we end up with our radius of convergence being 1, but our interval of convergence actually being from -1/3 to 5/3. Okay. All right, and so that's how we come up with that. So now that we know what our initial interval of convergence is, or the IOC prime, what we want to do now is test out, well, what is going to be the corresponding series that pops out whenever we let x equal -1/3 and whenever we let x equals 5/3, to see if those individual infinite series would converge or not. Okay, so I'm going to come here, and so we're going to say when x is equal to a -1/3, we're going to see what the corresponding series would be. So if we go ahead and put this together here, let's see what our original series was here. So this is going to be from 1 to infinity. And we're going to have 3 times a -1/3 minus 2. All of that raised to the n. All that over n times 3 raised to the n. And of course, 3 times a -1/3 is just going to give us a -1. -1 minus 2 is a -3. And so that's just going to give us a -3 raised to the n there. And of course, -3 raised to the n, I'll go ahead and write this here. -3 raised to the n can be rewritten as a -1 raised to the n times +3 raised to the n. Okay, so we're going to rewrite this numerator this way, and the denominator as n times 3 raised to the n. Okay. Now, of course, those 3 raised to the n's that we see there, they are going to reduce to 1. So we're going to go ahead and get rid of those. And what we have as a result is the alternating harmonic series. Okay. And so in my earlier videos, we've gone through the whole process of showing why, even though the harmonic series diverges, the alternating harmonic series converges conditionally because of the alternating series of the -1 raised to the n, the alternating sign factor that's a part of that. So in short, we know that if we were to look at the b sub n part of this, which is just the non-negative portion of this, which is just 1 over n, those values of b sub n decrease as n increases. And we also know that the limit of 1 over n as n approaches infinity goes to 0. So those are the two conditions that allow us to say that this particular series converges via the alternating series test. Okay, so the fact that the alternating harmonic series is conditionally convergent is well known. So again, I'm not going to go through the details of writing all that. But here we're going to say therefore, we'll say that this series converges conditionally via the alternating series test. Okay, and what that means for us is that this value of x equals -1/3 is in our interval of convergence. Okay, so now we need to figure out what happens when x is equal to a +5/3. Okay, so same thing. let's try that again. So here, when x is equal to 5/3, corresponding series that we're going to get, plug this in, we'll have 3 5/3 minus 2, and all of that will be raised to the n over n times 3 raised to the n. So 3 times 5/3 is 5, and 5 minus 2 is 3. So we just have 3 raised to the n over n times 3 raised to the n. And of course, those 3 raised to the n again are going to reduce to 1. And this time we have a pure harmonic series. And of course, we know that the harmonic series is just a p series where p is equal to 1, and it is going to diverge. Okay, so therefore, we know from here that x equals 5/3 is not going to be in our IOC. Okay, so therefore, we know that our IOC now is going to be including -1/3, will be excluding 5/3. Our ROC again is going to be 1. And so those were the things that we were asked to figure out here. And so with that, this concludes this example and concludes this video on looking at power series, figuring out what is going to be its interval of convergence as well as its radius of convergence as well. All right, so go ahead and join me in the part 3 video for power series. In the part 3 video for power series, what we're going to do there is talk more about how we actually use power series. And one of the main things that we use it for is to represent a function in a polynomial approximation. And so this is very useful whenever we have situations where we need to integrate functions that don't necessarily have what we call an elementary function antiderivative. Simply put, if we were trying to take the antiderivative of some function that we needed to integrate, and we couldn't do it by the hand methods that we know of from second year calculus, then we would kind of be at a loss unless we had another way of representing those functions. And of course, using power series is sort of our loophole to be able to do that. And so the part 3 video will start that conversation. So I hope to see you there.